Hi, in this lecture, I want to talk about density in function spaces. It's a particularly interesting topic because there are many practical function spaces, and I'll mention one example of a context that occurs very often in practice. So let's say fix X, the collection of images, collection of drawings, say, of numbers 0, 1, through 9. This could say be the collection of numbers as drawn in my lectures, because there probably does not exist a pair of my numbers that are both legible and actually look the same. But so let's fix this collection of pictures of these numbers, and we might be interested in functions that classify these. So we have a function fx that goes from x to the space 0 to 9. That tells us for each image, it outputs which number it is, which number is drawn. Now, the collection of such functions is, you could think of it as different algorithms or different ways of coming up with this answer. So you have actually a function space, f from x to the space 0, 9, that consists of all the functions f x to 0, 9. So you have a space of functions, and there is, in the space of functions, there is the real one that's really answering this question. And then, but we don't know that real one, and we can't hope to find that real one. Instead, what we find is f approximate. And this f approximate has to be computed by some algorithm, and we hope that the difference between f approximate and f real is small. So this is our hope. I mean, and here specifically, this approximating function is something we can compute. But if you look at this condition, approximating one compared to another element is less than epsilon, this is exactly the idea of density. So density comes into play exactly here. So now let's, I mean, this is the kind of the goal and the abstract motivation why we might think from a practical perspective about approximating things. But let's be a little bit, in this class, of course, we don't get quite that far. We're not going to talk about in detail about neural networks or machine learning or quality of statistical models, etc. But we are talking about a specific class of functions, so from 0, 1 to r. And this is kind of a simplifying context that allows us to talk about these issues, and you can extend all these principles to higher dimensions and to very different functions. In fact, these images, you can often think of them as a subset of Rn, and this is indeed a subset of R, so we're not very far from this. We've just simplified the domain to avoid some technical issues. Okay, so we are looking in the space of functions, and we want to approximate by, sometimes these are thought of as simpler functions, or you could also say more computable functions. So things that you can actually write an algorithm for that will evaluate. So one thing is that an arbitrary continuous function, just like an arbitrary real number, is hard to represent, say, in a computer, and there are different representations in practice that you might like that are also theoretically important because they have special properties that make them easier to work with. So one collection of functions that we might look at is polynomials, script fp. And this consists of all the functions, p from 0, 1, that are given by a polynomial. That is, p of x is equal to sum k equals 0 to n, or let's say d, the degree of the polynomial, and we have the coefficients a, k, x to the k. You could, to be proper, you'd say that there exists a d, there exists a1 through a0 through ad, real numbers. So we're looking at a collection of polynomials. If you wanted, you could restrict to rational numbers. That's another class, but okay, polynomials are one class of functions. I mean, if only for the reason that you have a very long exposure to them. You've seen them since high school, and yeah, at least high school. Now, there is another class of functions that is almost as good. So trigonometric polynomials, which is also looks a lot similar. And I mentioned it already now, even though I won't say much about it, is that these are functions that are particularly important for data analysis, physics, analyzing a lot of differential equations and behaviors, doing frequency analysis, stability analysis, structural stability analysis to see whether there are resonant frequencies in the system. This notion requires the idea of a frequency, and where it comes from is also this kind of approximants, except that we replace polynomials with periodic things. So t of x is a sum of periodic things. So there might be a constant part, but otherwise it's a sum of an sine 2 pi nx plus bn cosine 2 pi nx. And this is sum n equals 1 to infinity. So here it's analogous in that the simpler parts that we're kind of considering are sine and cosine, and the aspect that makes them a little bit simpler to work with is that they are periodic. But these are not very ideal. I mean, they do sometimes are used to, say, represent images, and certain applications such as medical imaging, actually they're quite important. But in, say, neural networks, or in if we want to classify digits 0 to 9, this representation of using either polynomial coefficients or Fourier coefficients, it's not ideal in practice. Instead, what has shown the greatest promise in the last decades is neural networks, as they perform very well in practice. And a simple case of that is a single layer neural network. So I will not talk about what is multiple layers. You can imagine that there are more of these, but how they behave, what they do. I don't want to get into those details, but I want to give a simple single layer neural network. So this consists of some functions. So you're computing a function that takes an input to an output. So an input in language neural networks, these talk about an input layer and an output layer. And an x is sent to a y, and how it is done, it's by a series of operations that behave like an algorithm, and represented by a network. So first, x sends its signal as an input to certain neurons, so you could think, or nodes. And what these nodes do is they take the input, they compute a certain function, an activation function, and they give an output. So the first neuron gives y1, the second neuron gives y2, and you have a large number of neurons, yn, and then you compute an output of them. And what you then do is you just sum up the signals and you take a linear combination. So sum of y, k, y is the output of this function. So this is a special class of functions that can be represented by such functions. And these activation functions, they're motivated by activation in biological neurons. So if the potential is bigger than something, then it gets activated, otherwise it doesn't activate. But of course, there's some transition region that is modeled, and somehow often with a sigmoid function is in practice quite often used because it's smooth. but you can use other functions. And so in general, you have some activation function. S is a standard, is the shape of the function. And then you have parameters here that you get to optimize, BI and AI. AI is a shift corresponding to the level of activation. And BI corresponds to how wide this shift is. You could also put the BI here if you want, because this is just a linear thing here. But for now, let's keep it like that. So there are variants of this. I'm not certainly representing all of them. Now, if you vary the parameters n, so how many neurons you have, and you vary the BIs, the AIs, and the WIs, you get different functions. And you could take the collection of all functions that are computable with a single layer neural network. You could take also the collection that are computed by a sec2 layer, n layer, but already a single layer is enough for our purposes today. Now, what the famous Weierstrass approximation, this is or in the case, or it's sometimes called the universal approximation theorem, is saying that all of these three classes that are important in different parts of mathematics and applications are dense. So in a sense, a function can be replaced by one of these classes. So f of fp, ft, and fn are all dense in X, in the function space that we were working with. So any function can be approximated in any one of these ways. Now, a little bit about terminology. Weierstrass usually refers to this first case. The universal approximation theorem usually refers to the third case. This middle one has different names. You could also, sometimes general Weierstrass theorem is used there, but it's also okay. This case, it's not always the standard way Weierstrass is stated. Weierstrass is usually stated for polynomials, but there are other cases when it's true. Now, why is this important? So I will not prove this full theorem, don't worry, and you're not expected to know its full theorem. The only case I will prove is the neural network one, because it introduces some nice ideas, and because many of you might like to know that as an argument. So, but what's the significance specifically of this neural network one? Is that it tells us that any function on a closed and bounded interval can be learned. Now, a small thing here is that actually you can make this a subset of Rn, or you can take a compact subset of Rn as well, if you want, and you replace that interval with that. All of these are still true. The proof that I give is only for the interval 0, 1, but you can imagine how it's generalized to other intervals, a, b, and there are some ways that this could also be generalized to higher dimensions, but I don't, again, as said, I don't want to get to that right now. Partly because if we had multiple, we'd have to introduce multiple layers here as well on the first layer to represent an input in higher dimensions. Now, so specifically, it means that any function can be decomposed into simple parts, xn, sine x over t, and these can often be analyzed, say, sines with signal processing. X to the n are, say, also easy to differentiate and integrate. So x to the n leads to numerical differentiation, numerical integration methods. Approximating by sine leads to, say, solving partial differential equations, or etc. And another thing is that while general data is often difficult to store, this gives different ways of storing the data and the function in the computer memory. So one can say store the Fourier coefficients. One can store polynomial coefficients. That's usually not a very good thing to do in practice, but it's possible. And for a neural network, we can store this information of this architecture. So the BIs, the AIs, the WIs, and of course an implementation of the and choice of the activation function. So and a small thing for this density here, you do need some mild assumption on the activation function. I'll be precise on what will at least work. Almost any activation function actually would work, but so I mean, except the constant function, say. So, but there are other mild assumptions that are usually satisfied, say, with all the common ones that occur in practice. But this is a statement of this theorem. In a separate video, I will prove the universal approximation theorem. So this FN case of density.